Hello everyone. Welcome to the day 20 of the Machine Learning Teach by Doing project. In the previous lecture, we learnt about regularization and we looked at the intuition behind regularization and why regularization actually helps us to prevent the model coefficients from becoming too large. This helps us to prevent overfitting, or it really helps us to prevent capturing the noise in the data. Overall, regularization pushes our machine learning algorithm to become simple so that we can have a good performance on the test data. If you want to have a clear understanding of regularization and why the regularization term looks like this mathematically, where this is the magnitude of theta, what is lambda, etc., I really encourage you to take a look at the previous lecture. It's a short lecture, but it will really give you a good understanding of regularization, which will help you follow today's lecture. So, what we will be doing in today's lecture is that we'll be taking the concepts which we learned yesterday and we will be having a practical implementation of regularization with a complex data set in Python itself. So this is the hands-on tutorial where I'll be going through a data set, and through this process you will also learn about feature selection, feature representation, and the choice of lambda in regularization, why regularization is needed, etc. We will compare without regularization and with regularization as well. So many people have commented on YouTube about the need for features and how to select features, which power of the features to use, etc. So we will get that clarified also in today's lecture. So let's get started. First, I want to show you the data set which we are dealing with. The data set looks something like this. uh, there are two classes of the data set. This is the first class, which kind of looks like it's spread in the inner circle, and here is the second class, which kind of looks like it's spread on a circle of a larger radius, which is a bit outside. In an Excel format, this data looks something like this. Here you can see up till the row number 58, we have a data set which is numbered as 1, and from row number 58 to row number 118, we have the data set which is numbered as 0. So this is the data set which we will also be importing it into Python, but visually it looks something like this. It looks like the data is spread along concentric circles. um, okay, then the goal is that, imagine someone is asking you this in an interview. uh, think of yourself as an ML engineer. So I'm asking you that, based on this data set, generate a classifier for the above data set. So let me also show the x and y axis here. This is x2, sorry, this is x1 and this is x2. Okay, so imagine you are a machine learning engineer and you have been asked this question that you have to generate a classifier for the above data set. The first thing which you should notice is that the classifier, the decision boundary will not be a straight line here. The decision boundary will not be a straight line. Uh, it looks like the decision boundary has to be a curved boundary here, which probably looks something like this visually. And it does not look something like a straight line. So the representations which we have earlier, theta 1 x1 plus theta 2 x2 plus theta not equal to 0, won't work here. Now, this immediately should lead you to your next conclusion as a machine learning engineer, that you will need to use the feature representation trick here. You will need to use the feature representation trick. Remember what we saw for features before? that data which does not look to be linearly classifiable. So this does not look to be linearly separable, right, in two dimensions. So data which is not linearly separable, or data which does not look like it can be linearly separated in two dimensions, we can project the data from a 2D space into a higher space and try to find the separator over there. This is the feature representation trick. We have a video for that in one of the previous lectures of the course, so I encourage you to check that video out. But feature representation helps us to take data which is not linearly classifiable in 2D space, project it onto a higher dimension so that it is linearly classifiable. This is pretty understandable, right? Because let's say if you do not project the data into higher dimensions, and let's say if your features are just one, x1 and x2, this is the order 1 feature. These are also called order 1 features. uh, Order 1, which means I'm not projecting it to a higher dimension. I'm not using the feature representation trick. Using this order, the classifiers which you will be able to construct will look something like something theta 1 x1 plus theta 2 x2 plus theta not equal to 0. So they will look like straight lines. And we know that straight lines in 2D space will not separate this data. So we should not restrict ourselves to order 1 here. We should look at higher orders. So order 2 looks something like this. This means projecting the data to a higher order space of dimension 2. So here we will not only have one x1 and x2, but we will also have x1, x2, x1 square, and x2 square. So due to the addition of squares, now the underlying equation can look a bit more complex. The underlying equation can look like theta 1 x1 plus theta 1 x1 plus theta 2 x2 plus theta 3 x1 square plus theta 4 x1 x2 equal to 0. It can look something like this. And this looks like it's parabolic, it's a bit more complex. So hopefully it can classify this data. Remember, we are in a circular space, it looks like here, right? So x1 square plus x2 square, that's the equation of a circle. X1 square plus x2 square equal to some radius. So intuitively it looks like we definitely need to have x1 square and x2 square. So it looks like we definitely need to go to order 2. We will also explore higher orders in our code, but just to show you a mathematical uh, version, as you go to higher orders, the number of terms which we have, they go on increasing exponentially. So right now in order 2 we had how many terms? 3, 4, 5, 6, right? In order 3 you will see that you will have much more terms. You will not only have the terms which you had in order 2, but you will also have these terms: x1 square, x2, x1 x2 square, x1 cube, and x2 cube. These are 9 terms. This is for order 2. In complex machine learning algorithms, as we'll also explore today, we can even go up to order number 20. Imagine the number of terms which will be present in order number 20. But some machine learning algorithms require us to do that. Remember that in machine learning, we have no problem with being in higher dimension space. Machine learning can be thought of as an act of converting lower dimensions to a higher dimension space. Even neural networks do that. Neural networks take an input, let's say, of 2 dimensions, expand them into higher dimensions, and then again bring it down to 2 dimensions. It's just that as humans, we cannot imagine spaces more than dimensions 3. So on the whiteboard, we can only have representations for dimensions 1, 2, and 3. So the second intuition we have with respect to this data set is we definitely need to transform our data using this feature representation trick. And these type of bases are also called as polynomial feature basis. This is called as polynomial feature basis, where the order 1 means polynomial of order 1, order 2 means polynomial of order 2, order 3 means polynomial of order 3, etc. The third thing which we will need to be doing is regularization. As we saw in the last lecture, in regularization, our objective function, let me pull up my notes over here. In the regularization, our objective function looks something like this. J of theta is equal to minus 1 by n sigma. This is the cross entropy loss function into uh, log of h plus 1 minus y into log of 1 minus h. But this objective function does not stop here. We have one additional term here, which is lambda into theta square divided by n. This is the objective function which we will minimize. So the only addition is this part. This is also called as the regularization term. This will be added. So now let us compare how the different things look like for regularization and without regularization. So I'm going to make a table here right now. So let's say we have no regularization in one case and we have regularization in the other case, and I'm going to compare the following quantities. I'm going to first compare the loss. So let us see what the loss will look like. So in the case of no regularization, the loss looks something like this: minus 1 by n. As we saw, this is the cross entropy loss, sigma y log h plus 1 minus y into log of 1 minus h. Correct? Whereas in the regularization, it will look like minus 1 by n sigma y log h plus 1 minus y log of 1 minus h plus lambda into modulus of theta square divided by n. Remember that when I am saying h here, I mean the sigmoid hypothesis. That's the first quantity which we compared. The second quantity which we will compare is the gradient. So when we don't have any regularization, we have seen in one of the previous lecture that the gradient term actually looks something like this: x transpose h minus y, where h is just the sigmoid, which is sigma of x theta. Now if you have the regularization, this term will look like something like this. The first part will remain the same, plus there will be an additional component here which will need to be added, and that component will look something like this: plus 2 lambda theta upon n. So here let me call it theta tilde, because here we have to basically put the bias term to 0. So the entire theta will remain the same, but just the bias term will be clipped off and it will be put to 0. That's why I'm calling it theta tilde. So you can see that the gradient term is exactly the same, except for the fact that this additional quantity has been added here. That is because you try differentiating this with respect to theta, you will get something like this written in the matrix form. And finally, the gradient update will look something like this. The gradient update theta I plus 1 is equal to theta I minus alpha times x transpose h minus y by n. So this is just subtracting alpha times the gradient, and here it will be theta I plus 1 is equal to theta I minus alpha times x transpose h minus y by n plus 2 lambda theta by n. So here we are just so let me add the alpha will be here also, alpha, because the alpha, which is the learning rate, will be multiplied on both sides. uh, Great. So in the last step, I have just used the same gradient as above, but added the learning rate parameter over here. So in the entire process, in all of these algorithms, if you see in the regularization term, so sorry, if we use without regularization, there is only one hyperparameter, which is this learning rate. Whereas if you use regularization, there are two hyperparameters. There is lambda, and then there is also the learning rate. So just keep these quantities in mind so that when we look at the code, you will appreciate the code much, much more. If you remember, if you remember these terminologies, or if you remember these quantities correctly. Uh, okay, so now we will be jumping into Python code for this particular data set, and we will be doing feature representation on the data set. We will be doing two cases. First, we will be showing the results with no regularization, and second, we will be seeing the results of regularization. We will explore using different features how having the different order changes our model prediction. We will also explore the effect of this lambda parameter here, and overall we will explore the effect of no regularization versus regularization. So let us get started. Great. So I have jumped into this code right now, which is in VS Code, and I'll also be sharing this entire code with you. So no need to worry about that. Let us understand this code step by step and what we have done. First, we load the required packages. Here, we have been using NumPy and Matplotlib pretty much all the time throughout this series. But today, I have loaded one more package here, which is called Seaborn. And Seaborn is an amazing Python package for plotting. So you can just head over to Google and search Seaborn in Python, and you will see that it's a very good packaging tool for data visualization. And using Seaborn, you can generate some wonderful data visualization plots. Then I have also imported optimize. I'll show you where this particular function is used. In fact, I don't think I'm using it anywhere, so we can probably remove it also. So let me first run this first code block. That is done. The packages are loaded. The second step which we need to do is load this particular data set. So this is the data set which is in CSV format, what I have shown you over here. So please look at this code and try to understand what I have done here. So np.load txt, which means that it's a txt file and I'm loading this particular file, correct? And then I'm just extracting the x data and the y data. So let me run this and show you what x and y look like. So if I plot x, it will look something like this, which is the x1 and x2. So it looks like, so this is x1 and this is the x2, which is the x coordinate of the data and the y coordinate of the data. So similarly, I think we have around 120 data points. So this is the x, and if I plot y, it will look something like this. So y is the true label. So the first 58 points will be 1, and the next 58 points will be labeled as 0. So look at how we have extracted the data here, and how we have generated the input data and the output data. That's the first step. Another step is that here I showed you this visualization, right? But when in real life you're given the data, you will just have the CSV file. So see how many things we understood from the visualization. We understood that the linear classifiers won't work. We understood that probably an order 2 would be needed since the data looks to be circular, correct? So that is why visualization of the data is so important. So we are using the Seaborn command called SNS here. So SNS, the command is scatter plot, scatter plot. We are basically just plotting the data. So if I plot this, it will look like this. What I showed you basically, it looks similar to this. The orange data points are classified as 1 and the blue data points are classified as 0. It looks like the orange data points kind of lie within an inner circle and the blue data points kind of lie within an outer circle. Clearly from this data, it is not linearly separable. Now, we are going to be using logistic regression, and just like we have seen in this table over here, we will need three things. We will need the loss, we will need the gradient, and we will need the gradient update. We already have the formulae for all of this, so we have no reason to worry. Also, wherever I have written h here, it's the sigmoid function. So of course, we'll need to define the sigmoid function initially. So here you can see that when we get started, first we define the sigmoid function, which is 1 upon 1 plus e raised to minus z. If you have forgotten what the sigmoid function visually looks like, it looks something like this, where this is 1 and it crosses the x equal to 0 at zero point 0.5. This is how, so if you have z and this is sigma of z, mathematically this function is 1 upon 1 plus e raised to minus z, and my hypothesis is sigma of x of theta. In one of the previous lectures we have seen that this x is an augmented x where we add a column of ones to the x data. So the x data actually 1 1 1 1, and then we have x1 x2 similarly. So we add this column of ones, and the reason we do this is because we have assimilated theta naught within the theta vector itself. So instead of having the theta vector and the bias term separately, this one theta now contains theta 1 theta 2, and it also has theta naught in that vector itself. If we did not have this augmented term, we will need to have a separate theta 1 theta 2 vector and a separate theta naught vector. But this, what it does is that it merges everything into one theta 1 theta 2 and theta naught, and that really helps the calculations. Okay, so first we have defined the sigmoid function here. Next we will define the loss function. Now look at what the loss function is. Loss function is minus 1 by n sigma y log h plus 1 minus y log 1 minus h. And h is sigma of x theta. This is exactly what has been done here. First you define h. H is sigmoid of x dot product of x and theta. And then you calculate the loss like y into log h plus 1 minus y into log 1 minus h, and you divide by minus 1 by n. Length of y is basically n, which is the number of data points which we have. This is exactly the same formula which we had written here for the loss function. Then we have to write a formula for the gradient, and we have already defined that here. The gradient is just simply x transpose h minus y divided by n. So if you see the gradient here, x transpose h minus y divided by n. And first we define h as the sigmoid of x multiplied by theta, or the dot product between x and theta, which is exactly what we had written here. Great, so that's out of the way. The sigmoid function is defined, the cross entropy loss function is defined, and the gradient is defined. Essentially we are all set now, except for the fact that we have not done the feature trick yet. Remember, we have to do a feature transformation here, because order 1 will not work. So here is a code which has been written, which implements the feature trick for any particular order. So if you look at this code here right now, what it does is that it takes x1 and x2, and it also takes another parameter which is the power. This power is basically just the order which I have mentioned over here. Basically, if the order is equal to 1, this function will return three terms, 1, x1 and x2. If the order is equal to 2, this function will return six terms, 1, x1, x2, x1, x2, x1 square and x2 square. If the order is 3, or if the power is 3, this function will return 9 terms, as I've written here. So this function is written such that we can specify any power here, and it will return those many feature metrics. I am not going to go into the mathematics of how this particular code has been written, because I think that is besides the point. I do not want to show you right now why this is x1 into I minus j, etc. You can figure that out on your own. It's pretty simple when you write it on your own. Just start with power equal to 1 and write down what this loop says one by one on your notebook. You'll understand what has been done here. Essentially, we are starting with an array, and so let's say if you have power equal to 2, step by step new elements are being added into the array. First 1 is added, then x1 is added, then x2 is added, then x1 square is added, then x2 square is added, then x1 x2 is added. That's what this np.append is doing. So this is my feature expand feature function, and this will allow me to convert my data set into other features, which will expand it from a two dimensional space to a higher dimensional space. Okay, then what we do is we define the gradient descent. So up till now we have defined the loss, we have defined the gradient, but we have not defined the gradient update. This is what we'll be doing now. So up till now we have defined the loss, defined the gradient, but we have not defined the gradient update. This is what we'll be doing now. So here is the function. It exactly follows this. We will just take the theta and we'll subtract alpha times x transpose h minus y by n. So that's exactly what's done here. You take theta and you subtract alpha times x transpose h minus y by m, where m is the data size, length of y, which is the length of the data set. That's it. So this is the update rule in the gradient descent. And now we define the final function which brings everything together, which is logistic regression. It takes in the argument as input data, the output data, the power which we want to define for the feature trick or the order as I have written in the whiteboard. Alpha is the learning rate, and the number of iterations which we want to pursue is 100. So essentially, there are actually three hyperparameters here. Earlier, I had mentioned that there is only one hyperparameter learning rate, but actually there are three hyperparameters. There is the learning rate alpha, there is the order of the features, and then there is the number of iterations. And we can vary all of this to find a good algorithm basically. Okay, so what this logistic regression does is that when it receives the data set, it first expands the features based on the order which we have defined. So what it does is that if this was not there, then it would just take the data set like it is. But it expands the features based on the power which we have defined. So if the power is 2, it will take it to a higher dimension plane. If the power is 20, it will take it to a 20 dimension plane. And then that's it. Then it just implements the gradient descent, and then it continues this loop step by step, and finally we have the updated theta, which is returned, or which is the final answer at the end of 100 iterations. Okay, now let us actually perform this logistic regression and implement it on our data set. So as a machine learning engineer, you have reached up till this point. You have defined the features, or you have defined a function. You have defined the final logistic regression function. You are ready. Now all you need to do is specify the hyperparameters. Uh, let's say the learning rate is fixed for now 0.01, which means that there are two other hyperparameters which you can vary. You can vary the power and you can vary the number of iterations. I'm going to start with a power of 20, which means I'm going to expand the data into 20 dimensional data set. As humans, we cannot even imagine what this will look like, and it will probably contain hundreds of thousands of features. A power of 3 itself contains 9 features, so you can imagine what a power of 20 will contain, how many features. And I'm going to do this for 20,000 iterations because this data looks to be a bit complex. Uh, so let's go ahead and let's implement this algorithm for a power of 20, number of iterations as 20,000, and here the learning rate I'm using as zero point 0.6 just for reference. So I'm going to run this piece of the code now. You see it's taking a bit of time because we have 20,000 iterations which need to be completed. Usually machine learning algorithms won't run as quickly as what we had earlier demonstrated on toy problems or toy data sets, and they do take some time, especially if you have a larger number of iterations. That's why if you have a computer or a CPU with a higher processing power or with a higher processing speed, then it's generally good because if you have large amount of data, it can process that data relatively quickly or in a relatively short amount of time. Okay, so it has been completed. It took 1 minute and 20 seconds for the computer to run this, and I've printed the accuracy right now. The accuracy seems to be 86% on the data set, which is quite good, which means it classifies 86% of the data set correctly. The last step which we have to do is visualize the classifier, which means we take the data set and then we plot the decision boundary. You can have a look at this plotting function. I'm not going to explain this function, but I'll just mention the things which I've used a function called as contour, which gives me a contour plot between the data and my prediction value through my classifier, and that helps me to plot the contour for the classifier. And then I plot the contour on the scatter plot of the data. So let me click on this run function to visualize the contour now. uh, so this is very important because this function will ultimately let you know how the decision boundary looks like. Okay, so it seems that our decision boundary looks like this, and you can already see that this is a very good example of overfitting. Our algorithm seems to have gone out of the way to really capture the noise in the data and really fit those things. So this is the perfect example of overfitting. See, everything looks to be constrained for the orange points around this circle, right? And this point which the algorithm has tried so hard to capture, what if it's just noise? Since we did not add regularization right now, our algorithm has essentially captured this noise also. That is a big problem for us, because let's say if I give you test data, up till now I've only shown you training data. But if I give you test data which lies somewhere here, let's say it lies here, the test data, it lies here, what is being shown in the arrow, uh, our algorithm will basically mark it as orange, but it clearly looks like that belongs to the blue category because the blue category is all spread out like this. Let me show you what I mean in this whiteboard actually. So let me go to this same plot which I have. Correct. Yeah, or let me just make a new plot so that the understanding will be easier. Okay, so what my classifier is doing currently is that it has these orange data points. It has these orange data points somewhere here, and the blue data points are somewhere here. Let me mark it in blue. The blue data points are somewhere here. Correct. Now, what my algorithm has done is that it actually has gone out of its way to even classify these 2 points over here. So, this is the boundary which it has made, uh, this boundary. So, the algorithm will classify everything inside this as belonging to the orange class. Now, think about a new point which is the test data, which I have given somewhere here, or if a test data is given somewhere here. It clearly looks like this test data belongs to the blue, right? Because the orange function looks to be in a circle of lower radius, and these points are maybe just the outliers. So the actual plot which we wanted was something like this, which should have ignored these 2 points as noise in the data. And if this was our actual plot, then these two green points would be correctly classified as blue. But now they will be wrongly classified as orange because our algorithm has overfitted and it has given importance to this noise in the data, and classified them as everything here will be classified as orange. That is what is meant by overfitting. And this is the main problem which arises if you don't use regularization. Now, what I'm going to show you is the exact same thing but with regularization. Not many things will change, as you will see. First, we'll define the cost function or the loss function. The loss function is also called as cost function sometimes. So, let us look at our table again, which is our reference point. The loss function is the same as the cross entropy no regularization loss, which is minus 1 by n y log h plus 1 minus y log 1 minus h. But we'll add this lambda times modulus of theta square by n. This is exactly what is done here. This is the cross entropy loss up till here. But we add one more term here, which is lambda times theta square by n. Correct? So this is the loss function which has been defined for regularization. Then now let us look at the gradient. The gradient for the regularization is x transpose h minus y by n plus 2 lambda theta by n, which is the same here, x transpose h minus y by n, this is length of y, plus 2 lambda theta by n. Now I told you that this is theta tilde, right? So the one thing which we modify in this theta is that we take theta but we replace the first element with 0, which means we are replacing the bias term with 0. Since we are taking the derivative, the bias term won't have, that will basically drop out. That's why it's called as theta 1. So theta 1 is same as theta but with no bias term there. So this is that additional term which is 2 lambda theta by n, which comes up in the regularization. This is exactly what has been written here, 2 lambda theta by n. The next thing which we will be doing is implementing the gradient descent. The gradient descent algorithm also is, we subtract um, this thing x transpose h minus y by n plus 2 lambda theta by n from the current value of theta and multiply it with the learning rate. This is exactly what is done. We take the theta and we subtract x transpose h minus y by n plus 2 lambda theta by n, where here it is written as m, which is the length of the data set. What is written as m here is what we had written as n here in this whiteboard. So this is the gradient descent, and the final logistic regression algorithm, or the final thing which puts all of it together, is the same as for no regularization. First we expand the input to a higher dimension space, then we implement the gradient descent. That's it. Then we keep on updating the theta, and then we return the theta, or we finalize the theta based on the number of iterations. Now you can see here that there are four free parameters, or rather four hyperparameters. So along with these three, so these three were there for no regularization. Along with these three, there is one more hyperparameter which is lambda, which is this parameter here. This that is for regularization, and this is also a parameter which we'll need to define before the training, and that's why it's called as hyperparameter. Okay, so now let us proceed with the training, and but first let us define the hyperparameters here. Let us define the same power and number of iterations as we had done above, 20 and 20,000. This is the same thing which we had done here, correct? And this is the same thing which we'll use here also. And we'll use lambda to be equal to 1. Let's just start with this to see how it is proceeding, and then we'll explore further. So let me now run this. Very similar to the previous run, this will also take a bit of time. Previously I waited for 90 seconds. I think this will also take roughly around that time, or maybe higher, because we are doing one more gradient uh, calculation which is needed for the regularization. So let me wait for that much time. Okay, so finally I could see that this iteration was completed, and it took a long amount of time. So I had loaded a previous version which I had worked on my system, and I'm presenting that to you right now. But remember that running this algorithm can take a bit of time, so please be patient. Um so here, first of all, I can see that the accuracy is 72%, which is a bit lesser than the accuracy which I had obtained earlier. And this is generally the case with regularization. In regularization, we don't try to fit the entire training data exactly, and so it we take a hit on our accuracy. Uh, so it took around 5 minutes 5 seconds for me to run this thing, which is more than two times what it took to run the previous one, because here probably more gradients were calculated, so it took more time. But the accuracy is less. That's the first thing we see. Now let us visualize the results. Um, So I have clicked on this particular visualization, which is the same code as what is for the previous. Um, so here you see this is how the decision boundary looks like. Can you see how different it is from the decision boundary which is here? What this decision boundary has done is that look at this point, this point. Look at this orange point. This decision boundary has classified this point as noise, and it has not at all tried to fit that point. This is amazing, right? Now consider a training testing data which lies somewhere here. In this particular case, that point will be classified as blue, which is probably correct since all blue points seem to lie here. But if we were to take the previous case, and if we look at a point here, this point will be classified as orange. This is the disadvantage of overfitting. And after we used regularization, our model accuracy is definitely reduced. That is fine. We don't need to fit all the training data accurately. We need to make sure that our model is simple and it is generalizable enough, which means it does a good performance on the testing data. I hope you are able to see the advantages of regularization right in front of your eyes using this. One more thing which I want to show you all is that one more thing which actually contributed to overfitting is the use of the order. So in this case, we used an order of 20, right, which is very, very high, and it gave us an accuracy of 85.59%. That also might have led to overfitting. What if we are in a huge high dimension space and that's why we are trying to fit everything exactly? Let us try to have just two. Let us try to just have the power of two here, and let us try to see the accuracy. So I am going to run this logistic regression right now. This code. Uh, so let me run this part of the code again. But now I'm going to play around a bit with the order, and I'm going to show you how the feature order can also have an effect on overfitting. Okay, so everything else is the same. It just I have reduced the order from 20 to 2. And here you can see immediately I finished this iteration in 2 seconds. Earlier it took 90 seconds. One more amazing thing I want you to see is that the accuracy did not change at all, which means there was no reason why we are using a power of 20. It led to a tremendous increase in computational time, a 40 times increase, because I was getting a 90 seconds of runtime earlier. Now I'm getting just 2 seconds. And let us visualize the classifier. Did you see the difference? Now it is not classifying this point as noise, or now it is not classifying this point. Now it is exactly same as the regularization case. It has recognized that this point is noise, so it should not be included in the classifier. It is probably noise, so it is fine to not fit this point. This shows that increasing the order of the features also leads to overfitting. Now we reduce the order, correct? We reduce the order from 20 to 2, and we have reduced the problem of overfitting. Now the decision boundary does not unnecessarily try to fit this point. This is very similar to the decision boundary which we got here. Plus, we also have a higher accuracy over here. This gives a very important lesson to all of you that when you select the number of features, please make sure to select it accurately, because the higher features you choose, it may lead to a good fit of the training data, but it will lead to overfitting. That is the first lesson. The second lesson I want to convey is number of iterations. So let's say I only had 200 iterations and I run this. So you'll see that the accuracy reduces a lot. And the classifier looks like this. Although it does not classify this point, which is good, but it also does not do a good job of classifying the other points, so the accuracy is reduced. That's why generally higher iterations is a good idea to get a good training as well as a testing accuracy. One more thing which I want to show you all is the effect of the lambda, which is the regularization parameter. Let's say if I put lambda to be equal to, now let's say here I am also using a power of 2 again, and let's say I use lambda as 5. Notice the earlier accuracy was 71. Now let us see the accuracy when lambda is equal to 5. Again, this was finished in 2 seconds compared to the 5 minutes it took earlier when I had a power of 20. Now, with a lambda of 5, I get an accuracy of 74, which is also a bit less. Let me try a lambda of 50. With a lambda of 50, you see we drastically reduce the accuracy. Can you try to predict why increasing lambda reduces the accuracy? Okay, so look at this. The more we increase the lambda, the more this algorithm will give importance to minimizing this aspect of the loss function. So the more we increase the lambda, the algorithm will give a preference to minimizing this a lot compared to this part. So even if the loss function is higher, uh, it will probably lead to a lower overall loss. So it's a summation of two terms, right? It's a summation of the loss function plus the regularization. So so let's say this is the case 1 where lambda is equal to 1, whereas this is the case 2 where lambda is equal to 50. Okay, so if we have a lambda equal to 50 as is shown over here, um, our algorithm will give a lot more priority for minimizing this term rather than minimizing the loss. So that will compromise our training loss, and that has the potential to make the training loss much higher. Um, and that's the reason why we should not have too high of a lambda also. There should be a balance between a low lambda to prevent overfitting, and a high lambda is not very good. Very high lambda is not very good because it leads to very low training loss, very high training loss. As we saw here, increasing the lambda to 50 really reduced our accuracy, whereas if you reduce that same lambda to 1 from 50, you will see that the accuracy increased by 30 percentage and the result remains the same. Let me try reducing the loss for, lambda further to zero point 0.1 here. So now lambda is zero point 0.1 and the accuracy you see has increased, and overfitting is also avoided since we don't capture this point, which is very good. Let me try reducing lambda even further to 0.01, and here we can see accuracy increases to almost exactly the same as what we had before for the no regularization case, and we still have the same function with no overfitting. This means that the ideal lambda for this problem probably lies around the range of 0.01. So this is the effect of hyperparameters when you are considering real life situations like this. So in this particular example, we saw three things. First, we saw regularization versus no regularization. In particular, if you don't have regularization, our model overfits by capturing noise, something like this. Whereas if we do have regularization, our model neglects these points. So although training accuracy is low, it's fine, but it neglects these points so that generalization and forecasting can be better. Second thing which we saw is regarding hyperparameters, and I just want to make a special note regarding the same. Whenever you encounter any machine learning problems, you are likely to face these hyperparameters: number of iterations, uh, learning rate, feature dimensions, and the lambda, which is the regularization term. It is very important for you to carefully select these four parameters. As we saw, if you look at feature dimension, if you have higher feature dimensions, it can lead to overfitting. Learning rate, if it's very low, it can lead to low train accuracy. Sorry, this for number of iterations. If the number of iterations is very low, it can lead to low training accuracy. And lambda, if it's very high, it can lead to low training accuracy. And if it's very very low, that is also not good because then again it will lead to overfitting. So we really need a good balance for all these parameters. Similarly, for the learning rate, if it's very low, then it will be slow. If it's very very high, then we'll get low accuracy. So as a machine learning engineer, one of the key skills which you will need to develop is how to select the correct value of these hyperparameters for the different problems which you are looking at. And I have seen that best ML engineers really have developed an intuition of the best values of these parameters. But you have to have a fundamental understanding of the effect of these hyperparameters on overfitting, the effect of these hyperparameters on training accuracy, training loss, etc. And I hope I have conveyed this to you in today's lecture. So that brings us to the end of today's lecture. Thank you so much, everyone, for attending this. And up till now, we have done an extensive work on classification. Overall, we have done about 7 to 8 lectures on classification. And now I think we are ready to move towards regression. So we are following the MIT's course now. Um we are also following a Microsoft's course parallelly, but it does not have too many good fundamental things. So we have finished up till week 4 of the MIT's course, and now we'll be moving to week 5, which is regression. So thanks everyone for staying with me throughout this course. I plan to make it as intuitive, visual for you as possible, and not just writing equations which you don't understand. My focus is on explaining everything from scratch so that you don't forget ML. And if you are asked questions in an interview like how to select feature dimensions, you should be able to answer those. Thank you everyone, and I'll see you in the next lecture.